Hi everyone, it's Miss H, and today we're going to be starting our new unit on motion. This unit's going to be divided into 4 videos, including the first one, which is our introduction with a bunch of terms and how to solve speed and velocity problems. Our second one, which will be about acceleration. Our third will be on position time and velocity time graphs, and then our final one will be on momentum. So let's go ahead and get started. First, you have to understand that there are 2 quantities that we use to describe the motion of an object. The first is called a scalar quantity. Scalar quantities describe only the magnitude or size. So how big is the motion? It only talks about what the size of the motion is, nothing else. Then we have vector quantities that look at both the magnitude and the direction. So how big is the movement and what direction did the movement go in? So how big and how far, so how far and what direction rather. It's important to know that scalar and vector terms don't just apply to motion, but that's the unit we're in, so that's how we're going to be applying them. The first term we want to talk about is position. So position is the location of an object at one specific moment in time. Think of it as a snapshot. So for example, Jim is 2 miles north of the store, Carla is 1.5 meters to the left of Anna, Manuel is 5 meters from the finish line. There's always some arbitrary 0 point here that helps us to reference where they are at. But that's it. It doesn't tell us anything beyond where they're at. So I'm looking at a picture. I know what's happening right here. I don't know what happened before or after. I don't know how they got to that position. I just know where they are right now. It can be positive or negative. Typically, we consider forward, right, up, north, and east to be positive directions, backward, left, down, south, and west to be negative directions. But depending on where you make that arbitrary 0, those could be the other way around. Just typically in this class, assume that if I'm saying north or east, it's moving in a positive direction. If I say left or backward, it's moving in a negative direction. We're always going to use the variable in this class of a lowercase d. Sometimes you'll see x when you look at other reference materials, but our state uses d as the variable on your reference table. So if you look at your reference table, you'll see your lowercase d to mean position, and that's going to come up again when we talk about speed and velocity. The second term we want to look at is distance, which is how far an object has traveled. So for example, Bianca drove 15 miles, Jeffrey ran 400 meters, Carson jumped 3 feet. All I know is how far they went. I don't know anything else about that. I don't know what direction they went in. I don't know whether they went in a circle. I don't know whether they ended up and finished at the same place or ended up and started at the same place. All I know is how far they went. It's always a positive number, which means that it's an example of a scalar quantity. It takes account the entire journey. So even if Bianca drove around in a circle, she still went 15 miles. It takes into account her whole driving distance, not just where she started and ended up. So for example, I have a mouse here, and here's its starting point. Okay. It's going to walk 1 meter to the left, then it's going to walk back half a meter to the right, and then it's going to walk another meter to the left. This mouse traveled 2.5 meters because it takes the entire distance from start to finish into account. It looks at the entire journey, not just one thing. The next term is displacement. So displacement is how far the object traveled in a given direction. Examples, Young drove 15 miles east, Salazar ran 400 meters to the right, Missy jumped 3 feet forward. Now I don't really know how far they went, but what direction they went in as well. So this can be positive or negative, which makes it a vector quantity. Again, so that would mean that Young and Missy and Salazar all went in positive directions, so we would keep them as positive numbers. Again, I could arbitrarily have made those be negatives, but for the sake of ease, we're just going to make them all be positive. It only takes into account the initial and final positions. It doesn't take into account the rest of the journey. So if we look at our same mouse again, okay, so the same mouse again, this time goes our 1 meter, and then goes back half a meter, and then goes back out 1 meter. So the mouse traveled 2.5 meters, but its displacement was only 1.5 meters because its displacement takes into account only the start to finish. It doesn't care about the rest of it. So it went forward 1, backward 0.5, and then forward 1 again. So 1 minus 0.5 plus 1 is 1.5. Or you could think of it as the distance from start to finish is 1.5 if you don't take into account how you got there. So it wouldn't matter if that mouse walked around in 10 circles, It just looks at where did it start, where did it finish. If they start and finish are exactly the same position, then the displacement is 0. So think about running laps around the track. If you start at the same position that you finish in, it doesn't matter how many laps you ran, how many miles you ran, your displacement is 0. You might have a distance of 5 miles, but your displacement is still 0 because you started and ended in exactly the same place. Next term we want to look at is speed. Speed is how far something travels in a given amount of time, or we can think of it as how fast. This is something we're pretty familiar with. Okay, speed is always positive and therefore is a scalar quantity because, again, speed just looks at how far and a certain amount of time. It just looks at the how far part, and time is always, always, always positive. We can't go backwards in time no matter how much we wish we could. Okay, the variable for speed is a lowercase s. The unit for speed is some form of distance divided by some form of time. Most often we're going to see meters per second, but we could see miles per hour, kilometers per hour, feet per minute, any type of distance unit divided by any type of time unit. The formula for speed is the absolute value of the change in position over time. Remember that little triangle is the Greek letter delta, and it means change in. You should have learned that in one of your math classes. Those two vertical lines are the symbol for absolute value. Again, something you should have learned in your math classes. So the formula for speed is the absolute value of the change of the position over time. Or another way to say that is it's looking at distance divided by time because distance is always positive. Now, on our reference table, this formula is not provided because they're just expecting you to use the velocity formula and ignore the directional component of it. So that's pretty much what we're going to do in this video as well. The last term we want to look at is velocity. So velocity is how far does it travel in a given amount of time and what direction does it travel in. So that directional component is what makes the key difference between speed and velocity. Now, normally we use the two terms interchangeably, and usually it doesn't really matter which one it asks for. You could use either formula as long as you remember to include direction if it asks for a velocity. So velocity can be positive or negative. That makes it a vector quantity. The variable is a lowercase v. The unit, again, is some form of distance divided by some form of time. Most often it will be meters per second, but again, it could be kilometers per hour, miles per hour, meters per minute, whatever. The formula for velocity is velocity equals the change in position over time. Again, notice we got rid of the absolute value here because it is possible to have a negative change in position and a negative velocity. Now, one of the things that we're going to do when we solve these problems is have this triangle helper here. So this little triangle is going to help us solve our equations. And the way that it helps us solve our equations is that we take our formula and we write it into our triangle. So I put velocity in the bottom and time in the bottom, and my change in position or my displacement in the top. And that's because displacement is in the top in this formula, so I needed to keep it in the top when I put it in the triangle, so that if I cover up my V with my finger, I end up getting d divided by t right back, which is the formula I started with. If I didn't put it in that way, I wouldn't get that same formula back. If I'm solving for velocity, I do displacement divided by time. If I'm solving for time, I do displacement divided by velocity. If I'm solving for displacement, I do velocity times time. Those are the same formulas I would get if I did this rearranging algebraically instead of using this triangle. This triangle is just a shortcut for me so that I don't have to do the algebraic rearranging every single time. All right, so now let's take a look at some examples. So Speed Racer completed the 30-kilometer race in 15 minutes. At what speed must he have been traveling to do so? So we're going to start by identifying some key pieces of information here. 30 kilometers is my distance, displacement, change in position, whichever term you're most comfortable with. I'm just going to stick with displacement for the ease here. 15 minutes is my time. Remember, time will always be measured in minutes, seconds, some form of hours, some form of time that you're used to dealing with. Displacement will always be measured in meters, kilometers, miles, something like that as well. And so we're trying to solve for speed, which we're going to just use the velocity for here for the sake of it's the formula we're given. So velocity is displacement over time. So that's going to be 30 kilometers over 15 minutes, and 30 divided by 15 gives me 2 kilometers per minute, and then I like to circle my final answer just because it helps me see that I'm done. Let's take a look at another example. Fred Flintstone drives to work at an average speed of 2 meters per second. How long will it take him to drive 4,000 meters? So 2 meters per second is my velocity, 4,000 meters is my displacement, and how long means that I'm solving for time. So I'm going to put this into my triangle helper here. V dt, scratch out my t because that's what I'm solving for. So t equals d over v, which is going to be 4,000 meters over 2 meters per second. My meters are going to cancel out, and that leaves me with 2,000 seconds for my final answer. Now this question didn't specify which unit of time I needed it to be in, so I can leave it as 2,000 seconds, but just because sometimes it makes more sense in our head to use change that to minutes or hours, if I were to divide this by 60 to get this into minutes, it comes out to roughly 33 minutes, which is pretty average for a commute in most places. Last example we want to take a look at. When spooked, Scooby-Doo is capable of running 7 meters per second. How far will Scooby-Doo get from the ghost if he runs for 35 seconds? So 7 meters per second is my velocity. 35 seconds is my time. How far means I'm solving for displacement. So I'm going to plug this into my triangle helper again. V dt, scratch out the d, so d equals v times t. So that's going to be 7 meters per second times 35 seconds. Gives me 245. My seconds are going to cancel out here. Meters. So 245 meters. That pretty much summarizes everything for our introduction. Our next video again will be on acceleration.